Hello, this is Professor Esther Pearson, and let's continue on in our Chapter 6 coverage of normal probability distribution. There are four basic types of probability problems. Number 1, probability less than some value. Number 2, probability greater than some value. Number 3, probability between two values. And number 4, probability less than one value and greater than another. Let's take a look at an example. Determine the probability. We have a deviation IQ scores, sometimes called Wechsler IQ scores. And they are scores with the mean of 100 and a standard deviation of 15. What percentage of the general population have IQs lower than 92? So we have our mean, population mean, using the symbol mu equals 100, and our standard deviation, population standard deviation, using the symbol sigma equaling 15, and our data value equaling 92. Using our z-score, our data value minus the population mean divided by the population standard deviation equals 92 minus 100 over 15. And that gives us a z-score of a negative 0.53. And that would give us a probability for a z-score less than a negative 0.53. And that would equal 0.298 or 29.81%. So when we answer the question, what percentage of the general population have IQs lower than 92, we see that 29.81% of the population have IQ scores lower than 92. For our next example, let's take a look at deviation IQ scores, sometimes called Wechsler IQ scores. And those are scores with a mean of 100 and a standard deviation of 15. What percentage of the general population have IQs larger than 130? So we have a mean of 100, standard deviation of 15, and our data element of x equals 130. Using our z-score, we have 130 minus 100 divided by 15, and that gives us a 2.00. And so for our probability, we see that 2.28% of the population have IQs larger than 130. Now we can take a look at how our tables can be helpful. What z-value has an area of 0.7357 to its left? If we take a look at that, we see that that 0.7357 intersects on our z values of 0.6 and 0.03. So the z-value is 0.63. Using our technology, our TI-84 plus, let's see what instructions we would follow. Press our second key, then vars. Choose 3. INV norm, open paren. The format for entering the statistics is INV norm, open paren area, close paren. In the previous example, we could have entered INV norm, open paren 0.357, close paren. Let's continue on using our table with another question. What z-value has an area of 0.0096 to its right? We see that we can capture it at 0.0096. So that indicates that we would have a z-score of a negative 2.34. However, the table assumes that the area is to the left of the z. And since the standard normal curve is symmetric, we can simply change the sign of the z-value to obtain the correct answer. So our z-value would be 2.34. Using our calculator, we can take a look at the instructions. Press the second key, then bars. Choose 3, which would be I and V norm open paren. The format for entering the statistics is I and V open paren 1 minus the area close paren. And the previous example, we could have entered I and V norm open paren 1 minus 0.0096, and that would have given us our answer. Now let's take a look at z-scores and percentiles. What z-value represents the 90th percentile? The 90th percentile is the z-value for which 90% of the area under the standard normal curve is to the left. We will look at 0.0900 in the tables, or 0.8997, which is extremely close to 0.9000, or 90th percentile. Doing so, we find z equals 1.28. Thus, z equals 1.28 represents the 90th percentile. Now let's take a look at a real-life example. Determine the following. The body temperatures of adults are normally distributed with a mean of 98.6 degrees Fahrenheit and a standard deviation of 0.73 degrees Fahrenheit. So our question is, what temperature represents the 90th percentile? For our solution, to determine the temperature that represents the 90th percentile, we first need to find the z-value that represents the 90th percentile. Once we have the z-value, we can substitute z, our mean, and standard deviation into the standard score formula and solve for x. Now from the previous example, we found z equals 1.28. Our mean equals 98.6, and our standard deviation equals 0.73. So we'll take our z-score formula, plug in our values. We know z equals 1.28 equals our x value, or the value we're solving for, minus our 98.6, which is our mean, divided by our standard deviation of 0.73, and that indicates that our x value equals 99.5344. So what temperature represents the 90th percentile? It would be 99.5344. Now let's take a look at another helpful statistical concept, student t distribution. The student t distribution is similar to the normal distribution in shape, but with more area under the tails, and is defined by the number of degrees of freedom. And we remember the number of degrees of freedom is represented by n minus 1, the total number of data values minus 1. So the properties of a student t-distribution are as follows. Number 1, a t-curve is symmetric and bell-shaped, centered about 0. A t-curve is completely defined by its number of degrees of freedom, or our d to f. Number 3, the total area under a T-curve equals 1. This sounds very familiar, doesn't it? And number 4, the x-axis is a horizontal asymptote for a T-curve. So let's make a comparison of the normal and the student T distributions. We see the normal in blue, and then we see our degrees of freedom equals 14 for the student T, and our degrees of freedom equals 3 for the student T on each side of this example. Using a table, the student T distribution table, we now have degrees of freedom as one of the categories. And if we look horizontally, we see 0.100, 0.0500, 0.025, 0.010, and 0.005 on our horizontal row. On our vertical row for degrees of freedom, we see 1, 2, 3, 4, and 5. This is just an example or a portion of the entire student T distribution table. Now let's continue on looking at our student T distribution table and get some nomenclature to go along with that distribution table. So for the student T distribution, the numbers across the top row represent an area to the right of T known as alpha. The numbers down the first column represent the degrees of freedom. Degrees of freedom equals n minus 1. Where the appropriate row and column intersect, we find the T value associated with the particular area and degrees of freedom. When calculating the T values, round your answers to 3 decimal places. Now let's take a look at some examples. Find the value of T sub 0.025 with 25 degrees of freedom. So we know our alpha is 0.025 and our degrees of freedom is 25. Here we can take a look at the student T distribution, and we find at the intersection of a degrees of freedom of 25 and an alpha of 0.025, we find the value 2.060. So our T of alpha 0.25 equals 2.060. Let's take a look at another example. How many degrees of freedom make T with an alpha of 0.010 equals 4.604. Now we've got our student T distribution table, and we take our alpha of 0.010, and we find our value of 4.604, and we see that that gives us a degree of freedom of 4. Great. For another example, we'll find the value of T such that the shaded area to the right is 0.1 for 17 degrees of freedom. So we take our student T distribution table, and we have our degrees of freedom of 17, and to the right, the shaded area to the right is 0.1. And we see that that gives us a value of 1.33. So our T with an alpha of 0.100 equals 1.333. And we'll continue on with another example where we'll find the value of T such that the shaded area in the tails is 0.02. Assume that there are 7 degrees of freedom. Now this type of problem is called two-tailed. If the area in both tails is 0.02, then the area in one tail would be 0.01. We're just simply taking 0.02 and dividing it in half so that we can get the area in each of the tails. Here we've got our student distribution table. And as we look at the alpha of 0.010 and the degrees of freedom of 7, we see that gives us a value of 2.998. So our t of sub alpha of 0.010 equals 2.998. And for our next and last example, find the value of t such that the shaded area between negative t and t is 99%. Let's assume 24 degrees of freedom. Now, since 99% of the area of the curve is in the middle, that leaves 1% or 0.01 of the area on the outside. Now, because the symmetry of each tail will only have half of 0.01 in its area, we have 0.005. We just simply took the 0.001 and divided in half. Now we've got our student distribution table, and we know we have a degree of freedom of 24. And we have our alpha value of 0.005, and so that gives us a value of 2.797. So for our t distribution value, we have 2.797.